On site, what one can procure are data points coming from experiments or observations. How do we differentiate them without any function? Learn it here in Numerical Solutions 2C problems. The set of approximate first derivatives contain three methods with 2 points. They are 2-point forward, 2-point backward, and 2-point central, followed by two functions involving 3 points. Then there is also 4-point central, making 6 functions to determine the rate of change or tangency. An application of numerical differentiation involves having only a dataset. Without any idea of the function, we can still determine the rate of change or tangency using approximation. Nevertheless, if one wanted to determine the function, use regression or interpolation, videos of which are posted previously. For the sample dataset, we are tasked to estimate the deformation at the instant when the load is applied, and the deformation after 3.5 days, where we are to employ 2-point central. The first requirement is to estimate the deformation at the instant the load was applied, and that was when time is 0. The dataset started at 0.5 days, with an increment of half a day. There are many points provided. However, what we needed should be extrapolated. So how do we use numerical differentiation to solve it? The priority functions to attempt are the central equations. There are two central functions in first derivatives. They are 2-point central and 4-point central. Between these two, the latter is even more accurate. So check if 4-point central is possible to use. With numerous points, include the unknown of x equal to 0. Then count at least 5 data points. In this case, it is possible. Starting from 0, include 0.5, 1, 1.5, until 2. These are 5 data points which include the unknown. This shows that we can indeed use 4-point central. However, this focuses on finding the prime of the central data point, and that is at x of 1.0. So we need to look for f prime of 1.0 first. Do the same check of using central first. With 2 points surrounding x of 1, we can then use 2-point central to look for f prime of 1. So use 2-point central, and its function is f of xi plus 1 minus f of xi minus 1 all upon 2h. Adopt the dataset into the function, and we get f of 1.5 minus f of 0.5 all over twice of 0.5. Now plug the values and get f prime of 1 as 145 less 52 all upon 1, which is simplified as 93. Knowing this value, we can then use 4-point central to look for the required deformation. The function is negative f of xi plus 2 plus 8 times of f of xi plus 1 minus 8 times of f of xi minus 1 plus f of xi minus 2 all upon 12h, which can then be interpreted as negative f of 2 plus 8 times f of 1.5 minus 8 times f of 0.5 plus f of 0 all upon 12 times 0.5. Place the values from the dataset, having 93 as equal to a sixth of negative 208 plus 8 times of 145 minus 8 times of 52 plus f of 0. We then get the deformation at time equal to 0 as 22. The next task is to extrapolate again the deformation when half of the days is still added to the test, thereby creating x of 3.5. Analyze the given. Which function can we use which includes the unknown? We can then use two options. One is to use 4-point central, just like how we solved the first task. Using this method, xi becomes 2.5, in which its f of prime can be solved using 2-point central. This is exactly what we did for the first requirement. In case one is wondering, how about the other option? Given the dataset, include the unknown attempting to use a central function. That would be 2-point central for this option. This function then makes x of 3 as xi. Then how do we solve xi? Since it is at the very end of the dataset, we can use 3-point backward to solve for its prime. Let's explore these two options to show the difference of the results. We start with a case when the deformation at x of 3.5 is solved through 2-point central. This means that x of 3 is xi, and its prime is solved using 3-point backward. Starting with 3-point backward, the function of which is thrice of f of xi minus 4 times f of xi minus 1 plus f of xi minus 2 all upon 2h. The adaptation to the dataset makes it 3f of 3 minus 4f of 2.5 plus f of 2 upon twice of 0.5. This is then thrice of 320 minus 4 times of 268 plus 208 all upon 1, which gives f prime of 3 as 96. With this value determined, move on to 2-point central to solve for the unknown. 2-point central is f of xi plus 1 minus f of xi minus 1 all upon 2h, which can be interpreted as f of 3.5 minus f of 2.5 upon twice of 0.5. This then becomes 96 as f of 3.5 minus 268 divided by 1. F of 3.5 is then 364. For the alternate solution, we again work on 4-point central to get f of 3.5. This tells that xi is 2.5, which can show that f prime of 2.5 be solved using 2-point central. Start by looking for f prime of 2.5 using 2-point central, giving the equation f of xi plus 1 minus f of xi minus 1 upon 2h. This is stated as f of 3 minus f of 2 over twice of 0.5, or taken as 320 minus 208 all over 1. F prime of 2.5 is 112. Having this determined, use 4-point central to tackle the unknown. Its function is negative f of xi plus 2 plus 8 times f of xi plus 1 minus 8 times f of xi minus 1 plus f of xi minus 2 all upon 12h, which can be said as negative f of 3.5 plus 8 times of f of 3 minus 8 times of 2 plus f of 1.5 upon 12 times 0.5. Plug the dataset values and come up with 112 as equated to negative f of 3.5 plus 8 times of 320 minus 8 times of 208 plus 145 all upon 6. F of 3.5 comes as 369. It has a difference of 5 from the previous calculation. And since we showed in the derivation that using central is more accurate, this is the most accurate approximation to the deformation.